Hi everyone, welcome to the first tutorial of machine design. Today we will be solving two questions in total. The first question is shown here. Draw the shear and moment diagram for the following shaft. The bearings at A and D exert only vertical reactions. If the shaft has a uniform diameter of 1.5 inch, determine the maximum stress due to the bending moment in the shaft. So here is the figure. They have mentioned that the shaft has a uniform diameter of 1.5 inches. The bearings at A and D, so these bearings, they exert only vertical reactions. So what do they mean by vertical reactions? The reactions are only in y-axis. And as you can see overall in this figure, there are no forces in the x-axis. So definitely there won't be any reaction forces in the x-axis. The other thing that they have asked us to find is the shear, to draw the shear and moment diagram for the following shaft, and to determine the maximum stress due to the bending moment in the shaft. So let's start by writing down what are given. So given the diameter of the shaft, which is equivalent to 1.5 inches, and we are also aware from the figure that the forces on gears FB is equal to 80 pounds and it's downward. Force at C is equal to 110 pounds and force at E is equal to 35 pounds. All are in the downward direction or negative direction. What are our unknowns? The unknowns are actually the reaction at A and reaction at D. RA and RD. Alright. So now we need to start with the first step, which is to draw a free body diagram. Okay. So how do we draw the free body diagram? We need to just draw the shaft as a straight line. You can mention the location of A, B, C, D, and E. Okay, and you can put the forces in there. So this is the force B, which is 80 pounds. At C, it's 110 pounds, and at E, it is 35 pounds. And we have reaction forces at D, so we can name it RD, and reaction at A, which we can call it as RA. So this is the free body diagram. So from this free body diagram also it is aware that the unknowns are RA and RD. One more detail that you can include in the free body diagram is the distance between the points. So this is 14 inches, this is 20 inches, 15 inches, and 12 inches. So now that we are done with step 1 and we know what are our unknowns, let's go to step 2, which is to apply the equations of motion. So what are the equations of motion? We have summation of force in x equal to 0, summation of force in y equal to 0, and summation of moment about a point equal to 0. But in our scenario, we don't have any force in the x-axis. So the equation summation of force of x equal to 0 is not going to be used. And how many unknowns do we have? Our unknowns are RA and RD. So we need to have two equations to solve this problem. So the equations that we may use is summation of force in y equal to 0. So we assume normally that upward direction is positive, and summation of moment about any point is equal to 0, and we assume counterclockwise as positive. Now, depending on your assumption, the positive sign or negative sign will affect. So now I'm going to apply the summation of force in y equation. So looking at the free body diagram, we have Ra, which is positive, minus force B, which is, I'll write it down as Fb for now, minus Fc plus Rd minus Fe is equal to 0. So in other words, we can write Ra plus Rd is equal to Fb is 80 plus Fc is 110 plus Fe, which is 35. So we have the equation Ra plus Rd is equal to 225. So this is equation number 1, pounds. So now we can apply equation number 2, which is summation of moment. Now you can take the moment about A or about D, because our unknown is located at these 2 points. So where you have the maximum number of unknowns, you can apply, but in this case the number of unknowns are the same at both the points. So we can take either one of A or D. So I'm going to take A. So summation of moment about A equal to 0 with counterclockwise positive. So let's see what these forces are doing about point A. So force B, it's going this way. So with respect to A, it is moving in clockwise direction. Force C is also doing the same. It's moving clockwise around point A. Force D, however, is moving counterclockwise, and force E is moving clockwise again. So anything that is moving clockwise will be negative, and anything that is moving counterclockwise will be positive. So I'm going to write it as minus FB times the perpendicular distance. So the distance from A, the point B from A is 14. And let's say the distance from C to A is 20 plus 14. D to A is the summation of these three, and so on. So FB times 14 inches minus FC times 14 plus 20, which is 34 inches, plus RD times 15 inches. No, not 15. You have to add the 2, so it's 49 inches, minus FE times 61 inches equals to 0. Now we are aware about FB, FC, and FE. Our only unknown is RD. So let's find out what is RD. So minus FB, so we can take the negative terms to the right. So RD times 49 is equal to FB is 80 times 14 plus 110 times 34 plus 35 times 61. So in the end, if you solve this, we get RD is equal to 142.76 pounds. So we got this as our equation 2, and we found RD. We can apply this in 1 to find RA. Okay, let's apply equation 2 to equation 1. So that gives us RA is equal to 225 minus RD, and that is equal to 82.24 pounds. So you can go back to the video if you want to see the previous notes, but I'm going to continue. So what is our next step? Now that we have all the unknowns, we can start with drawing the shear diagram. Okay, so step number 3 is to draw the shear force diagram or the shear diagram. So let's see how we can do this. Let's have the axis drawn first. So this is the x-axis and this is the y-axis, and this is the force diagram. So at uh, this location, let's mark the locations. So this is A, B, C, D, and E. So at A, RA is equivalent to 82.24. So let's draw a straight line. I mentioned this is 82.24. And at FB, it is 80 but in the negative direction. So we have to go down and continue this way. So 82.24 minus 80 is 2.24. And then we further go down to 110. So 2.24 minus 110, which will go down, and this value will become 107.75, 76 actually. And then at D we have the force RD equal to, we found it earlier as 142.76. So that will go up, and in the end we have the force downward. So this is actually 35 pounds as well. So again, the figure goes up when the force is positive. So we know RA is positive 82.25, so it is up. Then we have a force 80 which is going downward. So we subtract 80 and we have 2.24. Then further subtraction of 110 since it's downward. So it went to 107.75. And then we had found RD to be positive. So it goes up by that margin. And then it ends at FE is equals 35, which is going back to 0. So we can mark this location as positive, positive, this is negative, and this is positive. So this is the shear force diagram. Now from this, we can find, or let's say, I'll write it down on the other side. Step 4 is to draw the bending moment diagram, or the moment diagram. So how do we do this? One way is to calculate the moment at every single location, but better than that or easier than that is to just find the area under the curve. So from your shear diagram, the area under this will give you the moment value at point B, let's say. So I haven't labeled these points. So this is A, this is B, this is C, D, and E. So now what we'll do is we'll draw the similar graph here. So we have A, B, C, D, and E. I'll just mark them as points. Okay. So now let's calculate the area over here first to know the moment value at B. So this distance is 14 inches from A to B, and the magnitude or the value of the force is 82.24. So your moment over there would be 82.24 times 14. So it's as simple as that. To calculate the moment at a location, it is just to multiply or to find the area under the graph. Similarly, 2.24 times the distance between B and C. That is again 20 inches. This is 14 inches. And the third one would be 107.75 times the distance is 15 inches. And the third one is 107.76 times 15 inches, because the area between C and D, the distance is 15 inches. And the last one is 35 times 12 inches. So upon calculation, these values will yield to 1151.36. The units are important, it's pound inch, and this value is positive. The second one would be 44.8 pound inch, and again it's positive. The next one is 1616.4 pound inches, but this time it's negative. As we can see in the diagram, the area is negative. And the last one is 420 pound inch, and that's positive since it's again above the graph, above the line. So again, this is the shear diagram, and now let's get on to the draw moment diagram. So let's now continue with the moment diagram. Now that we have all the values, so at B the value is positive and it is 1151.36. So we just mark a point somewhere above like this, and we start from A and draw a line towards the point at B. The second value is 44.8. Now the thing to be noted is, since this is positive, you need to add the positive value to the next point. So point C is not 44.8, which is down. It has to be 1151.36 plus 44.8. There are some students which make this as a common mistake, so please be careful. Add these two values. So the next value will come out to be 1196.16. So the next value is 1616.4, but in the negative direction. So since the value is lower than, 1616 is greater than 1196, the axis will go to the negative axis. So let's put a point somewhere over here and join this 2, and this value is actually going to be 420, but in the negative direction. And then the last value, as we can see here, we calculated it to be 420, and always the moment diagram has to end at the 0 mark as well. So between these locations we can shade uh, the behavior. So here it is positive, from B to C it's still positive, and from C to D we have some region which is positive and some region which is negative, and from D to E it's still negative. Just mark this as D again. Okay, so now we have the moment diagram and the shear diagram as requested. The last thing that we need to find, or we can write it as step 5, is to calculate the maximum stress due to bending moment. So since they have mentioned that the maximum stress is due to bending moment, we don't need to look at the maximum value in the shear force diagram. We need to only look at the maximum value in the bending moment diagram. So what is the uh, M max is equal to 1196.16, right? I forgot to write down the values here. This is 1151.36, 1196.16. This is 420 but negative, and this is 0. So this is our maximum shear, maximum moment. So the value is 1196.16 pound. So now, how do we calculate the maximum stress? The maximum stress is equal to M max, which is the bending moment max, times C over I. So this is how we find the stress with respect to the bending moment. So this is equivalent to 1196.16 times C is the radius of the shaft. So we knew the diameter of the shaft was 1.5 inch. So the radius would be 0.75, and we have to divide this by I. I is the moment of inertia, and the moment of inertia for a circular section, because the shaft is circular, so for a circular section the moment of inertia is pi over 4 and r to the power 4. So that is 0.75 to the power 4. So this turns out to be 3.61 KSI. Alright, so that is the question 1. We can go back and just go quickly over the question. So, first of all, we identified what is given in the problem. Then we determined what are the unknowns. There are two ways to do this. One is to read the question and identify the unknowns, or the second way is to draw a free body diagram and determine the unknowns respectively. And once we have done with the free body diagram, we can apply the equations of motion depending on the number of unknowns we have. So in this question, we have two unknowns. So we need two set of equations to solve the problem. So we have two equations which we can apply. One is not applicable since we don't have any load in that axis. So we applied force in y, moment in at point A, and we found the unknowns. And once we found these, we were able to draw the shear diagram. So the shear diagram is as follows, as we explained earlier. And by finding the area under the curve, we can determine what is the moment value. So according to the direction of the normal force, from the normal force diagram, we can understand the direction of the uh, moment diagram. And once we get these values, we can just plot them in the same manner. And one more thing again to note is that you have to continue from the starting point. So this is 1151.36. The second one, the value is 44.8, but you have to add these two, which came out to be 1196. The third one is subtracting because it is negative. So 1196.16 minus 1616.4, which will come out to be 420. And then you go back to 420. And once we finish this, we have to calculate the maximum stress due to bending moment. So we look at the diagram, we check where is the maximum moment. So it was located here. Although we calculated this to be negative, but from the diagram, we can see at a critical section, the maximum is 1196.16. So we use that value and we go to sigma max equation, which is the maximum stress equation, and that is mc over I, and we applied this in order to calculate the maximum stress. If you are asked to find the maximum stress due to normal force or the shear, then you have to come back here and check which is the maximum value here. So the maximum value here was 107.75, and the stress equation would be sigma max equals the shear over the area, V over A or N over A, the normal force over area. I had forgotten to label the shear force diagram and the moment diagram. So in the shear force diagram, this is the shear force in pounds, and we assume upward as positive. And the moment diagram, we assume counterclockwise positive. And this is M, and the units are pounds, inches. So again, this is the x-axis and y-axis. And this moment is usually defined as the z-axis, which is the axis which is not labeled uh, in the diagram. You will see this later when we do a 3D problem. This is a 2D problem. Our next problem would be a 3D problem. So that's the end of question 1. Let's move on to question 2.